Hello everyone, welcome back to my YouTube channel. So today I'm going to do a simple video on how we can do a semantic search function using Elmo embedding. So before transformers, Elmo embeddings was very famous, and so the Elmo embeddings, biLSTMs, BiDAF, these are some of the popular architectures which people were using before the rise of all these transformer models. But still, these embeddings have good purpose, and like it is being widely used in different applications actually. So I thought I'll just show you guys how we can do some semantic search using Elmo embeddings basically. So first of all, to start with this particular use case, first we'll just touch upon what are word embeddings. So word embeddings are nothing but like a real vector representation of a particular word, or we can say dense vector representation of a particular word. So in this particular example you can see so that means like each of the words will be converted into a particular vector, learned vectors actually. So in this particular example, it's a very typical example actually. So the vector representation of man will be similar to the king. So the representation of each of these particular words will be lying together in a particular dimension space. So that's why we are calling these words as similar. So just like how humans are understanding man is to king, then model will also try to understand man is to king and women is to queen. So like that we can sort so many examples, and this is one of the table from Andrew Ng's lecture actually. So here he is actually transforming a particular word man into some 300 dimensional vector, and here you can see the dimension vector. So he just gave some hypothetical example like -1.0, 1.03. So these are the vector representations, and this is matching to the women. So that means this vector and the other vector are kind of like similar. So likewise apple and orange. So these both vectors have some sort of similarity. So now coming on to the Elmo vector. So Elmo is something like so it was very famous at that time actually. I think yeah. So it is by Alan NLP, and the documentations are actually available. And this is the typical structure of a by LSTM. So I think most of you guys are familiar with LSTMs and by LSTM. So they will be having two layer structure, and in each of the layer there is a forward pass and a backward pass, so that and there is intermediate vector inputs which is actually being populated, and that output along with the LSTM output, each of these layers is actually concatenated towards a final embeddings basically. So that's how this Elmo embeddings is being learned, and it is still very powerful. Okay, it's very powerful actually, and why? Because it's like it's having the understanding of the forward in the forward direction as well as in the backward direction, and we have multiple layers as well. So that's why it is still holding that importance basically. So now going on to how to embed using Elmo vector. So we have to actually load the Elmo embeddings from some source actually. So we are using something called TensorFlow Hub, which is kind of like a repository to hold so many models. So let me quickly open up TensorFlow Hub, and here you can see like different embeddings and different models are being loaded actually. So we'll go to the text portion, and here you can see like what are the problem domains. So we can actually check for our embedding. So let's say I need to have text embeddings, and here itself like there are different format as well, and the version, so which TensorFlow version. So it's actually a very good repository like our Hugging Face. So here I'm going to search our Elmo, and here you can see Elmo vector is here. So Elmo is having right now I think three versions, so V1, V2 and V3, and so the size is around 330 MB, and it is a language model trained on 1 billion word benchmark. It's a very powerful it's a very powerful embedding technique, and I've used in multiple applications where it gave very good result actually. So in one of my previous project, we were actually using Elmo embedding followed by a Distilbert embedding. So it gave that much efficiency in the problem statement, and it is very powerful when it comes to different problem set like multi-class classification and like semantic search and everything. So this is kind of like the example usage on how we can load the model. So here there are some yeah, change log and like different things mentioned in the paper. So it's a very good one actually, I would say. So now let's try to load. So before loading, we need to make sure like we need to install TensorFlow package 1.13.1. So make sure your TensorFlow is not greater than 2.0 for this usage actually. If it's, then you need to downgrade it. Then TensorFlow Hub, it's 0.7 version. And there is a module called Chart Studio which we are using for visualizing. So if you want to visualize using that, then you need to install this package as well. So let's install all the required packages here. So we need to install TensorFlow, TensorFlow Hub, then yeah. So Spacey I'm using to split the sentences. If you don't want to split the sentence using Spacey, you can just put some delimiter and split the sentences. That's up to your actually logic. So then I'm just giving some logging so that so whenever we load a model from TensorFlow Hub or TensorFlow, I think like there'll be so many warnings coming. So if you want to disable it, we can disable it this way. And so we need to run the semantic search similarity. So we need to have some cosine similarity function, and so these modules are for our, and for visualization I have TSNE and PCA. So PCA is nothing but to kind of decompress the multi-dimension to like some two-dimensional vector or something like that. So yeah, these modules are for visualization actually. So let's go on and try to run this particular block. So yeah, it will take little time to load all these models, basically TensorFlow and TensorFlow Hub. So that is our first step actually. And yeah, and I'm giving some additional removal for warnings as well using sys. So yeah, if you want, you can use it that way so that no warnings is coming, or else there'll be so many warnings like this package will get depreciated, something like that. So now let's just check what is the version. So TensorFlow version is 1.13.1 and TensorFlow Hub version is 0.7. Yep. So this is what it's required. Now I'm just loading some data called Marvel Data Store, which contains some data which I actually collated about some characters in Marvel comics. So I'm just running it, and I'm just pasting some of the descriptions actually. So it's talking about Thor and Loki and all those people basically. And now it's time to load the Elmo model basically. So I'm not doing data cleaning part. So if your data is messy, then make sure you clean the data in a proper format which you guys actually use in other applications. So I'm just leaving that part at this point because my data is somewhat okay. And then I need to load the Elmo model from the TensorFlow Hub. So as I said, I am loading this Elmo model from the TensorFlow Hub. You can either download it or you can actually call it from here. So in the URL itself, in the runtime itself, I am actually calling that particular model. So I need to run this. So it will take a bit of time if you are running it from the for the first time, because it's a 330 MB file actually. So it will take a little bit of time. Now what I am trying to do is I need to convert the paragraphs into individual sentences. And one thing to note is Elmo embedding, when we are actually embedding a particular word or a sentence using Elmo, make sure the word count or the token count is less than 150. Okay, so we should give that constraint. So so that is actually the advantage over the transform model. So models like BERT and other BERT variants has the capability to process 512 tokens. Okay, 512 tokens, and models like Elmo and other have like limited capacity. So we need to restrict that sentence count, word count in a particular sentence up to 150. So make sure you do that check. And so since my sentences are kind of small, So in a typical sentence, like it will not be extending to that much token length or something like that, but make sure you have that particular thing sorted. So I'm just joining and I'm just using spacey to kind of uh, convert them into kind of sentences. Okay, doc.sense. So spacey has this particular functionality to split the sentences. When we give a paragraph, it can actually split the sentences. So this is one logic. We can use other logic also. If you have a delimiter in mind, you can actually put it maybe full stop or whatever it is based on your data. So now let's go on and run this particular code so that you can see the sentences. So Thor Odinson is Asgardian god of thunder. So it is talking about some information about Thor, Loki, and all those people. So now let's embed the data. And what we have done previously is we collated all the data and we combined everything in a sentence list. So this is what we need to give the embedding to kind of embed, or the model to get embedded. So here this is the format to which we need to actually give. So embedding is equal to embed of, we need to give the sentences. Okay, so this is the place where we need to specify the list of sentences which we have to load. If you are using a GPU, you can create this tf.session in as a GPU instance. Okay, so before that you can actually write one line of config line and just give the GPU instance name, so that you can actually load this embeddings into as a you can actually run this particular thing as in a GPU instance, so that it will run much faster. Right now I don't have a GPU here, so I am just running it in a CPU. So it will take bit of a time because CPU this embeddings is actually very time consuming. And yeah, so if you have a GPU instance, better you run it in a GPU instance. Or if you are running in a collab also, that's actually fine. It will actually embed much faster, I think. So yeah, so always make sure like running embeddings is a very time consuming job. So you need to have the proper resource if the data is so lengthy. So luckily our data is small data set actually, so it ran faster. So now let's see. So here, if you see here, like each of the time we are opening the session, and there is something called session.run embedding. So X will contain nothing but the list of embeddings. So X is nothing but the array of all the embeddings. And let's see the dimension. So the dimension of Elmo vector is nothing but 1024. So there are around 50 sentences, and 50 sentences you can see it is each of the sentences are converted into 1024 dimension vector. Okay, so that is the dimension of Elmo embedding. So to visualize this particular embedding, like how each of the sentences are actually similar and everything, just like how I was telling about man to women and like king is to queen or whatever relation, just like that we can embed or make the sense of different sentences basically. So for that, let's try to visualize. So for visualizing, you can use PCA. Like this is just one technique. You can use any visualization method. So it's a very simple visualization actually. So using PCA, I'm just what I'm trying to do is I'm just reducing the 1024 dimension into 2 dimension. So here we can specify the dimension as n components equal to 2, and I am actually running that particular thing, and I have a plot here. So the plot will be yeah. So Elmo embedding representation in 2-dimensional vector. So each of these data points are nothing but sentences. So if you see here, let's take an example. So this green and green. So it is talking about in alongside Captain America and Iron Man, the latest sacrificing his life to eliminate Thanos and his armies. And this is talking about battle against Loki's army. So yeah, so maybe it's talking about the Avengers quest against each of the villains. So in the first series we have Loki, and in the third Endgame we have Thanos. So maybe it's correlating in that way, and you can see the relation basically if you kind of pan through all these particular data. Like you will get an essence of like okay what it's talking about. So it's talking about Dr. Jane Foster. Then it is talking about Thor Odinson, Asgard and Nine Realms. Then Mjolnir, his weapon, Loki Laufeyson. So like that, if you have so much information in your data, it will be kind of combined, and it will kind of make some sense to the information. So yeah, it is a very easy way to understand which all sentences are kind of correlated and how powerful these kind of dependencies are based on your Elmo embeddings. So it can be reused in any sort, okay, like not just Elmo embeddings, but any of the embeddings. So now let's see. So we converted our sentences into embeddings. So now how we will use it to make do our semantic search. So our application for like what we are discussing today is running a semantic search algorithm. So how to use this embeddings to run this particular thing. So there are so many use cases which we can actually use it from this particular point. Maybe we can build a question answering module. Maybe we can use a translation or modeling or summarization. Any most of the use cases, once we have the embedded data, there are some manipulations which is further required, but we can actually further perform it. So yeah, like there are some other use cases like translation and all actually requires a different set of logic, but still we can actually tell them like, okay, we can utilize the power of embedding. So the obvious use cases are like, okay, something which we didn't mention, like classification or like clustering, or those kind of things also can be possible, straight away possible. So now our portion. So we need to extract some sentences which talks about our query. So if I'm giving, so semantic search is that actually. So when we search something in Google, we will get something in return which is talking about that particular query, our query. So just like that, we need to extract some relevant sentences for a particular query what we have given. So the logic is something like this. So we have, for example, we have words like France and Italy. So if you see here, the theta value is close by. Okay. So the theta value is close by, and that means cos theta is kind of approximately equal to 1. So that means it is the cosine similarity, that similar nature of these two words are kind of close by. So that's what it's indicating in this particular plot. In this plot, it is actually 90 degree. That means there is no relation between ball and crocodile. So that is why it is tends to 0. That means there is no relation. Then there is something like pairwise relation. So France is to Paris, Rome is to Italy. So the two vectors are similar but opposite basically. So it's like country and its capital, like that. So it is close to -1. That means it is having that kind of opposite similarity. So now let's utilize how to make use of this logic to build a semantic search. So let's say I have a sentence called Thor Odinson is the Asgardian god of thunder, the former king of Asgard and New Asgard. Okay. Suppose I am giving who is thunder god. Okay. Thunder god query. So what ideally happens is this particular sentence will get embedded using Elmo embedding. Okay. And that will convert into a 1024 dimension vector. Similar to that, we will embed Thunder God using Elmo embedding, and that also will become an embedding of 1024 dimension vector. Okay. So now we have these two embeddings, and these two embeddings will be nothing but my A and B. So A dot B by modulus A dot modulus of B will be giving cosine similarity of these two 1024 dimensional vector. Okay. So finally we will get a value, like let's say if these two things are similar in the dimension space, the score is closer to 1. That means it is having high similarity. Okay. So that's how we will rank. So imagine there are like hundreds of sentences like this, and we are running the same query against all these sentences. So each time a cosine similarity value is being created, that means we are understanding that okay, this sentence and this word is having maximum similarity, or this sentence and this phrase is having lesser similarity. Based on that thing, we can rank the results basically. So now let's implement how we can do this. So I am asking a question like, who is Thor's brother? Okay. So if I am giving that query and I need to I need to embed this particular search string. Okay, just like how we embedded the sentences. So I'm embedding it. So this query is getting embedded. So it's a question basically. It's a search which we are giving, and the search vector will have the same dimension like how we had for our sentences or the raw data. So it is still 1024 dimension vector. Now I am running cosine similarity function. So when I am running cosine similarity, what exactly happens is each of these vector. So let's just see what is the output for cosine similarity vector. So if you see here, each of the query, that means that query is matched to each of the sentences, and it is actually giving a uh, cosine similarity score. Okay, how similar that particular vector is with this one. So we have the vector in this way, and now I'm just splitting and I'm just giving the output list. That means I'm just calculating which is the largest of it. That means which sentences has the largest similarity with the search query I have given. So now let's run this thing and let's output the list. So I have given search results as like top 3. I think I have mentioned somewhere here results returned should be 3. So in this code also results returned equal to 3. That means top 3 largest results. That means cosine similarity is high for those 3 sentences. So when I asked about who is Thor's brother, then the sentence which is kind of similar to that is Thor once tricked by his brother when Loki transforms. So that means okay, Loki is the brother of Thor. So it is picking the relevant sentence and giving it to us. So now let's search for what is maybe we can search for what is Thor's weapon. So ideally it should give either Mjolnir or a Stormbreaker based on the data which is available. So we need to repeat the steps basically. So yeah, okay, it's talking about Stormbreaker. Stormbreaker is an enhanced axe used by Thor. So it is understanding weapon. Okay, so axe is a weapon. So that means okay, it is understanding okay, Thor used this particular weapon. So Stormbreaker is the answer. So this is how it is actually kind of figuring out okay, what is the top result for a particular query. So you can use this, leverage this example in lot of applications, and you can actually come up with that particular similarity vector. So this is how we'll actually build a semantic search using Elmo embedding. So if you guys have enjoyed this particular video, then feel free to share this one, and yeah, just reach out to me if you have any queries with this. And thanks a lot for watching this video, and have a nice day. Thank you.